You think you know what an atom looks like. You've seen the icon 1,000 times. A little dot in the center, and a few smaller dots looping around it like planets. It's on textbooks, it's on science posters, it's on company logos. It's the universal symbol for physics. And that's exactly the problem, because that picture isn't just a simplified drawing, it's a story. A story that trains your brain to ask the wrong questions. And once you start asking the wrong questions, the atom stops making sense. You get confused. You get stuck. You start thinking quantum mechanics is just philosophy and weird words. So let's do something different. Let's build the atom again, from scratch, using only ideas that survive experiments. And I'm warning you now, your brain will try to fight this. Because the real atom is not a tiny solar system. It's not little balls spinning neatly in circles. It's not stuff the way you imagine stuff. The real atom is stranger. And the strangest part is this: atoms are the reason the world feels solid. Even though the solid part is basically an illusion created by rules. So what's actually inside an atom? Let's start with the simplest one: hydrogen. 1 proton, 1 electron. That's the atom we use to teach everything because it's supposed to be easy. And if the solar system picture is even slightly true, then you should be able to answer this simple question: where is the electron right now? Not generally, not around the nucleus. Right now. Where? Your instincts want to say, it's on the left side at this moment, moving along its orbit. But the universe doesn't let you say that. Not because our instruments are bad, because the electron doesn't come with a permanent location the way a planet does. Let me explain without mystical vibes. Imagine you're in a completely dark room, and you're trying to learn where a tiny creature is. Say, a moth. You can't see it continuously. You can only flash a light for a split second. Each flash gives you a single result. You saw it there. You saw it here. You saw it somewhere else. If you flash the light once, you get one location. If you flash it 1,000 times, resetting the situation each time, you can build a map of where it tends to appear. Some regions, it appears a lot, high likelihood. Other regions, it appears rarely. Some regions, never. Now here's the key thing that breaks your everyday intuition. In classical thinking, you'd assume the moth always had a definite position. You just didn't know it until you flashed the light. But in quantum physics, that assumption doesn't always hold. The theory we use, quantum mechanics, doesn't just say, we are ignorant. It says certain properties are not definite until an interaction forces a definite outcome. That sounds like philosophy, but it's not optional. It's built into the mathematics and confirmed by experiments. The tool we use to predict outcomes is called the wave function. And you have to be careful with that word, because it makes people imagine a physical wave, like a ripple in water. That's not what this is. The wave function is not a wave you can photograph in space. It's a mathematical rule that assigns a complex number to each possible outcome. From that, you get probabilities. So when people say electron cloud, the honest meaning is not a cloud of electron stuff, a cloud of probability, a map of where an electron is likely to show up if you try to detect it. And already, your brain wants to do something sneaky. It wants to say, fine, the electron must be somewhere specific, but we just don't know where, so we use probability. That's the classical instinct. But quantum experiments keep slapping that instinct in the face. Because the wave function isn't just a tool for ignorance. It behaves like something real in the sense that it interferes, spreads, and evolves in a precise way. Here's a simple question that exposes the lie in the solar system picture. If the electron is a tiny planet orbiting around the nucleus, then it is constantly changing direction. Anything moving in a circle is accelerating. Even if it keeps the same speed, its direction changes every moment, and accelerating charge radiates electromagnetic energy. This is not controversial. This is basic electromagnetism. So if an electron really orbited like a planet, it would radiate energy. If it radiates energy, it loses energy. If it loses energy, the orbit shrinks, and the electron spirals inward. That would mean atoms are unstable. They would collapse. But atoms do not collapse. Matter exists. You exist. So the orbit picture can't be what's literally happening. At this point, people try to patch the picture. They say, okay, so it's not orbiting. Maybe it's just sitting still, held in place. But that patch fails, too, because if the electron were sitting still at a point, you'd have two things at once, a definite position and definite momentum of 0. And quantum mechanics says you cannot have both perfectly definite at the same time. Not because you're clumsy, but because nature doesn't assign exact values to both simultaneously for a quantum state like that. This is the uncertainty principle, and it's often explained badly. A lot of people think it means your measurement tools disturb the electron. Yes, disturbance matters, but the deeper point is mathematical. Position and momentum are linked in the structure of quantum states. If one becomes sharply defined, the other becomes spread out. So, electron sitting perfectly still at a point isn't a stable allowed quantum state in an atom. So, the electron is not orbiting like a planet. It's not sitting like a marble. So what is it doing? Here's the most honest answer, and it sounds frustrating at first. It's not doing a classical motion at all. It exists in a quantum state described by a wave function, and that wave function has allowed shapes and allowed energies. Those allowed states are what we call orbitals. Notice the word orbital. It sounds like orbit. That's historically unfortunate. An orbital is not a path. It's not a trajectory. It's a standing pattern, like a vibration mode. If you pluck a guitar string, it doesn't vibrate in a random shape. It has allowed modes, fundamental and harmonics. In the same way, the electron in an atom doesn't take any arbitrary energy. It fits into allowed quantum states. The lowest energy state of hydrogen is a smooth, spherical probability distribution, not a ring, not a loop, a sphere-like pattern of likelihood. Higher energy states have patterns that look like dumbbells, clovers, donuts, lobes. But again, those are not electron shapes. They're probability patterns, built by repeating measurements on identically prepared atoms and plotting where the electron is detected. And here's something that feels like cheating. When the electron changes from one state to another, it doesn't glide smoothly like a car changing lanes. It transitions between discrete energy levels, and when it does, the atom emits or absorbs a photon whose energy matches the difference between the two states. That's not a story. That's a measurable fingerprint. If you heat hydrogen gas and look at its light through a spectroscope, you don't see a continuous rainbow. You see sharp lines, specific wavelengths, a barcode. Those spectral lines are one of the strongest proofs that atomic energies are quantized. The theory predicts them with extraordinary accuracy. So if the solar system picture were correct, you'd expect a messy range of energies, like planets can have any orbit. But atoms don't behave that way. Atoms behave like quantum systems with discrete permitted states. Now, I can feel your brain getting impatient. You're thinking, okay, enough with wave functions. What is the electron actually? Is it a particle or a wave? That question is a trap. It's like asking, is a shadow a thing or an absence? It depends on the situation. In some experiments, the electron produces localized clicks like a particle. In other experiments, it produces interference patterns like a wave. If you demand one label, you'll be disappointed. The honest answer is, an electron is a quantum object described by quantum rules. The wave function evolves smoothly, like a wave. But when you detect an electron, you always get a localized outcome, like a particle. It's as if nature runs a continuous calculation, then returns discrete results when you ask a discrete question. This leads to the famous headache. Measurement. Why does a spread-out wave function suddenly give a single outcome? What counts as a measurement? Where does the wave function go when it collapses? That's called the measurement problem. Physicists argue about interpretations, many worlds, pilot wave, objective collapse. But here's the key point for your viewers. No matter which interpretation you prefer, the predictions of quantum mechanics work, and the atom obeys those predictions. So if your goal is to understand what's inside an atom, you don't need to pick a religion about interpretation. You need to understand the rules. Now let's add more electrons, because the real magic of atoms shows up when you have many electrons. Helium, 2 electrons. Carbon, 6. Iron, 26. Suddenly you get chemistry, you get bonds, you get the periodic table, you get life. And the most important rule behind all that complexity is not electrons orbiting. It's a rule about identity. Electrons are identical in a way your brain isn't used to. Not similar, not same brand. Perfectly identical. There is no tag. You can attach to electron A that makes it fundamentally different from electron B. If you swap 2 electrons in a quantum description, the physics doesn't let you pretend nothing happened. For electrons, swapping changes the wave function in a specific way. This leads to a rule called the Pauli exclusion principle. No 2 electrons in the same system can occupy the exact same quantum state. This sounds technical until you realize what it does. It forces electrons to stack into different states. It forces shells. It creates the structure of the periodic table. It makes chemistry diverse. And it explains something you experience every day: why you don't fall through the floor. When you press your hand against a table, you might imagine hard atoms bumping into each other. But what you're actually encountering is mostly electromagnetic interaction between electron distributions plus exclusion pressure, preventing identical fermions from occupying the same state. Solidity is not atoms touching like billiard balls. It's fields resisting overlap and quantum rules forbidding certain configurations. The world feels solid because the universe has strong constraints, not because it's made of tiny, hard beads. And now you can revisit that famous phrase, "Atoms are mostly empty space." People love that line, but it can mislead you because it suggests empty means nothing. In modern physics, empty does not mean nothing. Even in a vacuum, quantum fields exist. The lowest energy state of those fields isn't a blank void. It has structure. It can fluctuate. It can produce measurable effects. So inside an atom, yes, the nucleus is tiny compared to the overall atomic size. But the region between nucleus and edge is not an inert nothingness. It's where the electron's quantum state lives as a probability structure. It's where the electromagnetic field exists. It's where interactions happen. So if you're trying to picture an atom as a few beads separated by absolute emptiness, you're still using a classical movie. Now let's go to the nucleus, because many people assume at least the nucleus is real stuff. A bunch of protons and neutrons packed together like peas. But even that picture isn't fundamentally correct. Protons and neutrons are not elementary. They are made of quarks bound together by gluons. And the quarks are not little marbles sitting still inside. They're quantum fields with interactions. They're confined in a bound state. The proton is better thought of as a stable pattern of energy and field behavior than a bag of 3 marbles. And here's an even more mind-bending fact. Most of the proton's mass does not come from the quark's rest masses. A huge chunk of the mass comes from energy in the fields and interactions, energy stored in motion and binding. That's E equals mc squared in the most literal way. So when you ask what's inside the nucleus, you don't end up with smaller and smaller hard beads forever. You end up with fields and energy patterns. At this point, you might feel robbed. You might want there to be something solid at the bottom, a final layer of real stuff. But modern physics points in a different direction. The best description we have is that what we call particles are excitations of fields. Electron, excitation of the electron field. Photon, excitation of the electromagnetic field. Quarks, excitations of quark fields. Gluons, excitations of the gluon field. The fields fill space. They're not sprinkled around like objects. They're everywhere. And a particle is like a ripple or packet of excitation in that field. So what is an atom? An atom is not a tiny machine with parts. It's a stable arrangement of quantum field excitations bound by interactions and constrained by rules. It's a pattern. And now, with that in mind, let's revisit size, because scale is where intuition really breaks. The nucleus is about 100,000 times smaller than the atom in radius. That means if you made the nucleus the size of a marble, the atom would be roughly the size of a stadium. And here's the awkward part. As far as we can currently tell, the electron behaves like a point-like object. Experiments have found no internal size. So you have something that behaves point-like, yet the atom occupies a huge volume relative to the nucleus. How can a point-like electron fill a stadium? Answer: it doesn't fill it as stuff. Its quantum state is spread as probability amplitude across space. Again, your brain wants a picture, but the picture misleads. What you really have is a rule for where it can show up when you measure. Now let's add another ingredient that gets misunderstood: spin. Spin is one of the worst named concepts in physics because it makes you imagine a spinning top. But if the electron is point-like, it can't literally spin like a ball. Spin is not a tiny rotation in space. Spin is an intrinsic quantum property with angular momentum-like behavior. When you measure electron spin along an axis, you get one of two outcomes: up or down, no in between. And before measurement, you don't get to say the electron secretly had a definite up or down along every axis. Quantum states don't assign definite outcomes for all possible measurements at once. So even the electron's internal orientation behaves in a way that has no classical analogy. Now let's talk about the part that usually gets people stuck. Why can't we just look inside the atom and see what's happening? Because looking is not passive. To resolve something small, you need short wavelengths. Short wavelengths require high energy. High energy means you disturb the system. You can't avoid this by building a better microscope. It's not a technology problem. It's a physics problem. At the quantum level, measurement is interaction. And interaction changes the state. So asking, "Where was the electron before I measured it?" can be like asking, "What was the exact face of a coin before it was minted?" The act that creates the definitive outcome is part of the story. Now, here's where the one-picture understanding becomes powerful. If you can't picture the atom as planets, how should you picture it? You should picture it like this. An atom is a set of allowed quantum states around a nucleus, governed by the Schrödinger equation in non-relativistic contexts, and more generally by quantum field theory. Those states produce stable patterns of probability and energy. Those patterns determine how atoms bond and behave, and the rules about identical particles determine the structure of matter. That's the atom, not little balls in circles. Now let's make this even more satisfying by connecting it to everyday reality. Why does chemistry exist? Because electron states can be shared, reshaped, and lowered in energy when atoms come together. A chemical bond is not a tiny hook. It's not little magnets snapping. It's a lower energy quantum arrangement. Atoms combine in a way that produces a more stable total configuration of electrons and nuclei. Electrons occupy molecular orbitals, states spread over multiple nuclei. That's why molecules have shapes. That's why water has its angle. That's why carbon can form chains and rings and make life possible. It's not marbles stuck together. It's quantum states reorganizing to minimize energy under constraints. And why do you get different elements? Because the nucleus has different numbers of protons, which changes the electric potential, which changes the allowed electron states, which changes chemistry. So the periodic table is not a list of different kinds of stuff. It's a list of different allowed electron state structures produced by different nuclear charges and the exclusion principle. Now go back to the very first lie, electrons as planets. If that lie were true, the periodic table would not look like it does. Chemistry would not behave the same way. Spectral lines would not be sharp. Matter would not be stable. Everything you recognize about the world is evidence against the solar system atom. Now let's address a final emotional issue. People hear all this and feel like physics is saying, the world is not real, it's just math. That's not quite right. Math is the language we use to describe the rules, but the success of the rules suggests there's a deep structure to reality that isn't obligated to match human intuition. Your intuition was built for survival on a certain scale: throwing, catching, running, climbing, judging distance, predicting arcs. Quantum reality lives at a scale where those instincts are not reliable. So it's not that reality is made of math like a fantasy. It's that the best consistent description we have is mathematical, and it predicts outcomes with astonishing accuracy. And when a description predicts reality better than your intuition does, you don't argue with reality. You update your intuition. So let's say it plainly. Inside an atom, there are no tiny solar system paths. There are quantum states. There are fields. There are constraints. There are probabilities that become definite outcomes only when interactions demand definiteness. There are rules that make matter stable and chemistry possible. And from those rules, everything emerges. Your table feels solid because electrons resist overlap and the exclusion principle forbids identical electrons from occupying the same state. Your body holds together because atoms can form stable quantum bonds. Light exists in discrete photons because atomic energy transitions are quantized. The nucleus has mass because energy in bound fields contributes to mass. The vacuum isn't empty because fields exist everywhere, even at minimum energy. That is what's inside an atom, not stuff the way your brain expects. A deeper kind of structure, a pattern governed by rules. And here's the weirdly comforting part. Even if you can't picture it perfectly, you can trust it because it works. It predicts the spectrum of hydrogen. It explains why the periodic table has its shape. It powers electronics, lasers, semiconductors, MRI machines. It's not a vague philosophy. It's a machine for accurate predictions. So if you feel uncomfortable right now, good. That discomfort is your brain realizing the textbook icon was a cartoon. The real atom is not a picture. It's a set of rules, and the rules are what reality is built on. If you want the next step after this, the next question is even more dangerous. If the world is quantum, why does it look classical? Why do we see one stable reality instead of superpositions everywhere? That takes you into decoherence, how interactions with the environment rapidly destroy interference between large-scale states, making the world appear definite. But that's for the next video. For now, keep one sentence. The atom is not a tiny solar system. It's a quantum structure, fields, states, probabilities, and rules, producing the illusion of solid stuff. And once you see that, you'll never look at matter the same way again.